Okay, so let me start by thanking Sanjib. It is a great opportunity for me and for his kind invitation. I have never ever been in India, so it's also first time for me, which makes it especially pleasant occasion. Today I will talk about some part of your colloquium which more concerns stochastic processes, and not even stochastic processes themselves, but some tools which people, especially experimentalists, use to operate and analyze the stochastic processes. The talk is based on two papers with my dear colleagues and friends, Alessio Squarcini, Enzo Marinari, Luca Pilitti, and Lamberto Rondoni. So, as Chiron gave the essence, the title is a little bit longer, but the essence is that to consider the spectral densities as random variables and what we can learn about them from such a perspective. If you open any textbook, and especially in engineering or whatsoever, you will read that the definition of the spectral density, standard definition, which is given in the equation in the first line. It is some function mu, which is a function of frequency. So it is taken as the limit of observation time t capital going to infinity. Symbol E capital denotes averaging over all possible realization of the process, and then there comes some variable which is realization dependent, which is written in the second line. This is fairly general definition, but if we talk about real valued stochastic processes, it simplifies like that. And then you see that basically if you perform averaging to get the standard result, you need just to know the covariance function of the process. That's it. And then you have to go to the limit t goes to infinity. You may immediately know that, for instance, if you set frequency equal to 0, then it will be just squared area under a random curve. So it already gives you some hint, and this is something which was well studied in the works of Satya, Gregory, and many, many others. So just in two words, to make a bottom line, standard definition is, for standard definition, you just want to know the covariance function and integrate from 0 to infinity. And evidently, upon some reflections, because usually engineers or experimentalists don't object the definition, it is given and it is taken for granted. But let us think a little bit about it. First thing, it is infinite t limit, which is a bad thing in two aspects. First thing, that no one lives that long and you cannot wait until infinity, neither in experiments nor in numerics, never. Second thing, that this limit is in fact very restrictive, because then, for instance, if you deal with super diffusion processes, often this standard definition gives you infinity. So this integral does not exist. And it may exist only for some class of stationary processes. That is why it is restrictive. And in this case, one resorts for other definitions of spectral densities, for instance, due to Wigner and Wheely, in which you go to minus infinity, you make it by hand, you make the process stationary, and so on, and this is more or less well defined. But this definition, of course, is very bad if you want to treat some experimental data, because you don't know what was happening there before time 0. And second story, of course, if you want to talk about random curves, areas of random curves, it makes no sense. So, second story is even more alarming, because in principle, this standard definition, it is just a first moment of some probability density function of this single trajectory random variable. And you don't know what this first moment gives you. Really, it can be whatever. Even worse, sometimes, and we know many situations in physics and mathematics when moments are supported by some tails of the probability density function, which in turn means that they are supported by some anomalous, not typical, and rare realizations of trajectories, which in turn implies that you have to have an enormous statistical sample, which is not always possible. Because in biophysics, for instance, when you do in vivo experiments, 5, 10 trajectories, and that is all what you can have. And in this sense, of course, it is good to know the full probability density function in order to estimate where from the values of the moments come and what should be bet and how large the sample should be. And you want to know, of course, some typical behavior of these power spectral densities. So the outline of my talk will be as follows. I will start just telling you how this standard μF looks like for a family of anomalous diffusion processes like fractional Brownian motion. And then I will go one step above. I will talk what no one never studied. It is about the say, standard deviation of these random variables and the ratio, noise to signal ratio of standard deviation of this random variable over the first moment. And then I will pass to general results, and I will show that first you can calculate the full probability density function for arbitrary Gaussian process, which might be not very surprising, but technically quite involved. I will discuss typical behavior, and I will also talk about frequency correlations of single trajectory spectral densities. So, no, it doesn't want. Oh, okay. So, fractional Brownian motion, it is the process as introduced by Mandelbrot and Van Ness in their famous paper. I will talk about one-sided version. So the covariance function it is a Gaussian process, non-Markovian with a long memory, and its covariance function is explicitly given by the expression in the first line. For time, if you define time strictly greater than 0, it is like this, but if you define on the whole real axis, you just have to take absolute values of T1 and T2 in two first terms. You may see that, for instance, setting times equal to each other, that for the mean square displacement, it gives in power T to H. H is the Hurst index. If it is less than 1/2, you deal with a super diffusion. And increments are positively correlated, which means that if you, on some previous step, you did this step in this direction, most likely you will keep on going like this. Now, for the case 1/2, it is standard Brownian motion without correlations. And for H less than 1/2, you have a subdiffusive behavior, which means that if you step like this on the previous step, most likely you will return back. There are plenty of realizations of this type of processes really in nature. It is not just a mathematical construction. And I will mention some of the examples after. So now we will look on the behavior of the first moment of the probability density of the single trajectory spectral densities. It means conventional distribution, standard distribution, except that we don't require that T is infinitely large. It is large, we take it large to simplify the formulas, but not infinity. So if we look on subdiffusion, we see that the leading term as a function of frequency, it is 1/2h+1, which, okay, if you are lucky and you can get it in experiments and you can calculate h and you can say that my motion, which I observe, is a fractional Brownian motion. The correction term in the limit t goes to infinity for f strictly than 0, it is here. And then there are terms which decay faster in the limit t goes to infinity. But you see that here the limit t equal to infinity exists. You just killed these two terms, and this is what you get. Brownian motion, standard result, which you can find in many textbooks, for arbitrary frequency n t and h equal to 1/2. This is this simple expression. You see that you can go to the limit t going to infinity, this term disappears, and this is famous 2d, in fact, over frequency squared, and this is the result, which is believed to be a fingerprint of Brownian motion. Finally, let us turn to the superdiffusive case, so h greater than 1/2 and less than 1. And, oops, and here you get, what is wrong with it? How one can return? No? Can you help me? No, it goes. Let me return a little bit. Yeah, here. So I cannot return, yeah, by the same button. And here you get that in the limit t goes to infinity and f greater than 0, the leading term depends on t. And the power in which frequency enters, it is 2. And it is pretty deceptive because many experimentalists treat the processes with spectral density of processes just looking on the dependence on frequency. And it is 2 here is pretty much deceptive because in reality, it gives you an impression that you deal with a Brownian motion, but it is not the case. To realize that it is superdiffusion, you have to redo measurements in different values of t and to see that there is aging. But coming back to what I said about restrictive limit, you see that if you put t capital equal to infinity, this is infinity, doesn't exist. Now we go one step beyond the conventional analysis. We look on the second moment of this random variable, calculate the standard deviation divided by, yes?
So, one slide back. When you said leading order terms, this was leading for large T and
Large T, large T. I say that it is bounded away from 0, and that's it. This is important, definitely. Limits are not commuting, especially in case of superdiffusion. There is no commutation of limits. Yeah. And so you look on this noise-to-signal ratio at the end. You can calculate it analytically, and these are wavy curves here for different values of H, Hurst index, thin solid curves here, which you see as simple asymptotics, which are written in the equation there. Numbers with errors, these are values of H, and simple amounts of Monte Carlo simulations. And what you see that regardless, yes, and this appears to be the function of omega, which is the product of frequency multiplied by the capital T, the observation time only. So frequency and T does not enter separately. So this, you see that there is some common behavior. All these curves for small frequency, actually frequency equal to 0, start from square root of 2. And again, we come to these curves, areas of curves under random Gaussian curves, which is fairly universal. But then they behave very differently. You see that in the superdiffusive case, 2/3, 3/4, and 7/8, there is a dip first, and then they start to climb back to the square root of T. In case of H less than 1/2, it is as exemplified here by 1/4 and 1/3, they keep on decreasing and approach the value of 1. But the borderline case, H equal to 1/2 standard Brownian motion, goes separately, absolutely, and reaches eventually the value square root of 5/2, a very strange number. And if you think about it, in fact, it is a criterion on anomalous diffusion. Because quite often in experiments, people see some exponent, what they call anomalous diffusion exponent, which deviate from 1, but only slightly. And they claim that it is either superdiffusion or it is subdiffusion, but not diffusion. But there is always a problem that the fitting window may be too small. You don't have many orders of magnitude over time, and so on and so forth. But if you do this kind of analysis, you will see that Brownian diffusion, whatever it happens there, it goes to completely different value as compared to superdiffusive and subdiffusive case.
Go ahead. So, why do you
I don't know.
Is there a case where you can have the situation for the other one, where you actually go below and then it goes back inside?
I don't know what this minimum signifies indeed. We thought about it, but we didn't find an answer.
Resetting systems, what we have seen is
It is a bit different story. It is not, because you see, you have this minimum, which say, for instance, for correlation function of something like Ornstein-Uhlenbeck driven by fractional Brownian motion, you have this deep, which is a measure of anti-persistence, but on contrary here, you have persistence. So I don't know to which this deep is attributed.
What about since you're in finite T here, what is assumed or implicitly assumed, maybe I'm missing something about initial conditions?
Initial condition, you start from zero.
So you assume this.
Yeah. You're fixed to start from zero. You see it from the no. I specifically said about t greater than zero version, which is called one-sided version of Mandelbrot. I don't take care about any what happens.
So you got rid of this complication?
Yeah.
Okay.
Yeah.
This was also important, because otherwise you would have been all this history.
No, I think my bet is that you will gain exactly the same story, but it's not an important issue. You will get the same for Riemann-Liouville version, which is on a finite time interval. So it's not an issue here. Okay. And so we did a comparison, actually, as a criterion of anomalous diffusion. I have plenty of my colleagues, experimentalists, like Matthias Weiss in Bayreuther Langen, who did recorded trajectories of telomeres in mammalian cells, or bits in viscoelastic media. It was Diego Krapf group. So Christine Zilhuber-Unkel from Heidelberg, she did some experiments on dynamics of amoeba and their vacuoles inside. And also Felix Retort joined us recently, and it was some anomalous superdiffusive dynamics on the cycloskeleton of actin. We also reconsidered, for instance, this work, this diagram which I showed you on the previous slide, in case when in experiments you cannot avoid having some position mistakes, dynamics or statics, and it appears to be pretty robust actually as a criterion. So, having given you an example, say, of for a family of processes, how this conventional property mu looks like, how the property noise to signal ratio based on the second moment looks like, I will pass to the general results, and I will now consider generally the spectral density of an individual trajectory as a random variable parameterized by frequency and observation time, and I will try to derive the probability, full probability density function for a important class of processes, which are Gaussian processes. So, first result concerns, and you will see that I badly need it, concerns the bounds on this noise to signal ratio. And so general result states that for arbitrary centered Gaussian processes, for arbitrary fixed frequency and observation time, this parameter is bounded from below by 1 and from above by square 2. Whatever the Gaussian process is, superdiffusive, subdiffusive. I will give you some hints on the derivation also of this inequality, because it has some instructive points, which can be, which are quite fancy. At least I like them very much. So you formally define the second moment of this random variable. You use the probability theorem of Wick, so you represent the fourth moment like this, sixth moment like this, and so on and so forth. At the next stage, you just rewrite formally the second moment in terms of integrals. You expand the cosine, like product of two cosines plus the product of two sines, and then everything can be reduced to this form where this averaged of SCC, SS, just it is for cosine, cosine, sine, sine, and so on and so forth. And then you get that the variable can be written, variance can be written like this. It is just very formal procedure. You recall next that in terms of these integrals, the first moment can be represented as the sum of CC and SS contributions. Then you take it, write it, and then you add and subtract the same term. And as soon as you get this term, you get the first moment. First term is first moment squared, and then you have a sum of two squares, which tells you that really it is positive, then the definite contribution, and it means that the variance is greater than the squared first moment, and so on. It is a trivial, pretty trivial result. But physically, it is incredibly important because it tells you that for any Gaussian process, the noise-to-signal ratio is bigger than 1. It means that fluctuations around the mean are bigger than the mean itself. And it tells you that it is not a good definition of the standard property, be constraining yourself to just to the first moment.
Do you have conditions for which this becomes an equality?
Frequency goes to infinity, observation time is large. Then you saturate the upper bound when you put the frequency equal to 0. For super diffusive case, frequency can be equal to infinity. It also saturates the bound. Yeah. This proof of the upper bound appears to be much more tricky. You do the same procedure. You start with the formal expression for the variance in terms of this SCC and SSS and SC integral. And now you have to prove that the variance is smaller than 2 squared first moments. You again add two terms, you subtract, you get on the right-hand side 2 squared first moment, but then there comes the term which you cannot say that it is negative. You have to prove it. In other words, you have to prove the inequality in the middle line here. Or if you return back to this explicit formulation of these integrals, CC, SS, and so on, you have to prove such a thing for arbitrary covariance function of a Gaussian process. And of course, it seems to be a hopeless task, absolutely. But not really. Recall the Mercer theorem from classical quantum mechanics 100 years ago, which states that if you have an arbitrary symmetric continuous non-negative kernel function, which is symmetric upon replacement T1 over T2, then there exists some orthonormal set of eigenfunctions defined on OT, in which the kernel function can be expressed as a factorized expansion in these eigenfunctions. Yeah? Then you denote Ck as the integral of this eigenfunction with cos, Sk as the integral of the eigenfunction with sin. You plug it back to this enormous inequality, and what you get, it is Cauchy-Schwarz inequality, which is automatically obeyed, which in turn proves the bound. So, our theorem number 2 is that for arbitrary centered Gaussian process, like Brownian motion, fractional Brownian motion, Ornstein-Uhlenbeck Gaussian signals, and so on, for arbitrary f and t, the probability density of this random variable, which is a single trajectory spectral density, is given by this compact form, which is the so-called Bessel function distribution. And you see now why I badly needed actually that gamma is bounded is greater than 1 and less than 2. Yeah. And it is monotonically decreasing function with an exponential tail of this form. Note that here value of s is divided by the first moment, I will return to this point later a little bit, what it signifies, but it is such a simple, rather simple function, I would say. So first, just to get you an idea how to derive this result. So you start from, can we come back? Now, you write the characteristic functional in which in the first line, in which you take the average of exponential minus some kappa, and this positive definite variable. Formally, it is the fourth of something which looks like action with a periodic kernel for a single trajectory, and you formally rewrite it. Again, writing cosine of the difference of 2 times, like a product, a cos of product, plus sinus of product. And then you go to the, again, mathematical science of 1930, something like that, which is called Karman-Loewe decomposition, which states that for any zero-mean square integrable Gaussian stochastic process defined on OT, it admits the following representations, where these are eigenfunctions from the Mercer theorem, exactly the same. And here, Zk are independent, normally distributed random variables with zero mean and variance lambda k. I will talk about it a bit later as well. And then you simply plug it inside the definition. You express your random variable s ft as the sum of these 2 squares, where this sum rounds over the variables zk and coefficient zk, which I defined already. Then you take advantage of the integral identity expressing Gaussian variables as simple exponentials. And you have an infinite integral, you perform that, and you arrive to this form, which is written here. And from the first conditions from the first theorem, we already know that this sum is positive definite. Otherwise, the integral doesn't exist. Then you do simple thing. You identify what does it mean sum over ck squared plus sk. It is just first moment in this representation. And the sum before kappa squared, it is this coefficient is simply 2 mu squared minus variance of s. Yeah, and it gives you the result which I just showed you. Now, once we have the full probability density function, we can ask about typical behavior. And typical behavior is formally, we instead of averaging the function itself or its moment, we average the logarithm and exponentiate it. The integral can be performed exactly, and this is what you get. Basically, you see that the typical behavior, it is, if you have just 10 realizations, it's enough to say something about average and so, but most likely this is what you will observe. And you see that it is proportional to the first moment, but it has an amplitude, numerical amplitude, which lowers it. And second, what comes here, it is a function of gamma, of the noise to signal ratio, which behaves differently for different frequencies. So this guy can be very different from what you will have by performing a full averaging. Next thing which is interesting, and what I briefly mentioned already, so this is the function which I showed you upon calculation of the integral. And you can look on some limits. When gamma, for instance, goes to 1, it is some far tail for subdiffusion. Then you see that it becomes a full square, and it is a simple exponential function in this limit. Or when gamma goes to square root of 2, so you look on very low frequencies, then the second term under square root vanishes, the coefficient in front of kappa squared, and you are left with this, which gives you the gamma distribution. And now we look, for instance, on this exponential thing. And you see that most likely the single trajectory density, it has the same dependence as its first moment, typically, because there is no other way to acquire. So it means that You may write it like exponential minus some b, which is some dimensional random variables which have the same distribution as the ratio of these two. And here you don't know what is it in fact, because it does not have any regular dependence on frequency. It can be only kind of a noise. It means that if you do, say, calculate the distribution for one frequency, not necessarily the b will here will be exactly the same as if you do it for frequency, for other frequency. And so we have three options here. So that b is some kind of a delta correlated noise in the frequency domain, and upon incrementing the velocity, we will have to set it in u. B is a noise, but it is correlated. And B is a random variable completely independent of F. It means that you have a completely correlated noise. And below, at the remaining time, I will, on example of four processes like Ornstein-Uhlenbeck, the model of Brownian gyrator, Brownian motion itself, and fractional Brownian motion, I will show that, in fact, all three scenarios are possible. So, what we are going to study? We look on this single trajectory power spectral density calculated at frequency 1, normalized on the first moment, multiplied by the same single trajectory power spectral density, but calculated for frequency 2, so it will be correlation function of such a form. And we will look on the Pearson coefficient, standard Pearson coefficient of two variables, S at F1 and S at F2, which are definitely linked to each other by this relation. And so if we have E equal to 1, so it will mean this E of BF1 and BF2 equals to 1, it will mean that complete decorrelation and that the Pearson coefficient is equal to 0. So summarizing the results, we consider first Ornstein-Uhlenbeck process and go to the limit of infinite observation time. What we get here for this correlation function, that it is equal to 1 if frequencies are not equal to each other and both greater than 0. Again, to the 1 if either of the frequencies is equal to 0 and the second is greater than 0. 2 if frequencies coincide. And 3 if both are equal to 0. A bit more complicated. So process B is a delta correlated noise in this situation. Positive definite. So it is not white. So we look on the Brown gyrator model next, which is two linearly coupled Ornstein-Uhlenbeck processes, each living at its own temperature. This I mentioned, just a second. Yeah. It's a little bit more complicated system with essentially out of equilibrium behavior. If you look on it as a coordinates of a particle on a two-dimensional plane, this thing will start spontaneously to rotate around the origin, and that is why the name of the model comes, the gyrator. But surprisingly, what you get for this model, it is exactly the same behavior for the Ornstein-Uhlenbeck process. Now, Brownian motion, completely different story. For unequal frequencies, both bounded away from 0, you have 3/2. Then if one of them is equal to 0 and the second is greater than 0, you have 7/4. If both are equal, you have 9/4. And eventually the same value as we had before for Ornstein-Uhlenbeck, for equal frequencies and both equal to 0, it is 3. And it is the case of squared area of under Brownian motion. Then there is some subtlety also for the Pearson coefficient, because if both frequencies are not equal to each other and bounded away from 0, the Pearson coefficient goes to 2/5. But if one of them is 0, it achieves a completely different value, which is 3/2 square root of 10, which is a little bit slower. So in this case, B is a correlated noise. But correlations depend on whether one of the frequencies is 0 and so on. Then we look on subdiffusive FBM, and what we get, exactly the same result as for Ornstein-Uhlenbeck process. Superdiffusive FBM, completely different story. As well as for Pearson correlation coefficient. So it is 1, so this process is like a rope, but if one of the frequencies is 0, then it has some lower value, so it is a partially correlated noise. In some cases, one of the frequencies is both frequencies are not 0, it is totally correlated, and partially for in the case when one of the frequencies is 0. And summarizing it here, we arrived at another criterion of anomalous diffusion. So if you have experimentally recorded trajectory for some process, so you may study frequency correlations of it. And here we can group the results. So Ornstein-Uhlenbeck, Brownian gyrator, and subdiffusive FBM are all three subdiffusive with mean square displacement growing slower than t. Brownian motion is a borderline case in which you have a completely different behavior. And finally, for the superdiffusive case, you also have a completely different behavior. So just studying these frequency correlations, you may say what indeed this process is. It is subdiffusion, it is Brownian motion, or it is a superdiffusion. Even if this, what they call anomalous diffusion exponent, only slightly deviates from 1.
This is again for T large.
This is for T large, yeah. So, just in summary, what is the main message to take? So, there are bounds on the noise-to-frequency ratio, which typically, absolutely, generically for arbitrary Gaussian process exceed once, which means in turn that fluctuations are stronger than the mean values. The probability density function of this random variable has a universal form regardless of the precise process, but it suffices to be a Gaussian process that it is what you get. And also frequency correlations show quite a non-trivial behavior and have completely different limiting values in case when you deal with subdiffusive processes, Brownian motion, or superdiffusive motion. So thank you for, let me just again acknowledge my co-authors, and thank you very much for your attention.
So let's say I'm looking at an experimental result where I can't really let the system have a go on for a long time period, okay, because of some limitation to my experimental setup itself.
Yes, definitely.
Then I do see the first result that you showed that typically the variation about the noise is typically more than the signal after. If you take a not very short time scale, then you start seeing that pattern. But I was wondering that if I have many particles, I'm looking at those particles and their behavior, but I only have a short time window through which I can observe. Is there some way I can...
It depends on the process. Certainly you can do it, and people do it for Brownian motion. If they have a long trajectory, they cut it into pieces and perform averaging in such a way. Or they take n particles simultaneously and record their trajectories and say that this is the same process. Hardly you can do it with FBM type processes which have memory on the entire past.
So that's what I was wondering, that if I, for example, took different trajectories from different particles and did a statistics on those, like could I think of piecing those trajectories together to think about a long-term behavior, or would I be losing information if I did that?
It is uncountable. In general, it is uncountable recipe. It is unjustified.
I have a related question. So suppose the mean square displacement shows some crossover behavior, so
Yeah.
the exponent changes over
Yeah.
time. How does this behavior look like in your gamma, for example?
It has, for instance, if you take into account something like in experiments you have position errors, yeah, which are, say, some additional random variable distributed like Ornstein-Uhlenbeck. It may cause, for instance, in the case of super diffusive case, it may bring you down from square root of 2 for the coefficient gamma. It may have an effect. It may have an effect because large frequencies, it is short time behavior.
Okay.
Short
Yeah. On the
frequencies.
other hand, when you described your results on gamma, I think you were emphasizing the asymptotic value, right? So is that criterion still useful when the crossover takes place?
Oh, you have to look on the plots which you obtain and analyze them.
Yeah, okay, of course,
what-
if the time range is wide enough, yeah. Okay, yeah, thank you.
So maybe a bit more technical question. So the the universal form that you proved for the distribution of the estimator, you said it's valid for any Gaussian process.
Yeah.
So, I mean, in principle, if I want to do it in the form of path integral, then what you are proving is that the propagator plus the perturbation can be diagonalized. That's a bit surprising.
If you have a Gaussian process, yes, it can be diagonalized. In general case,
Okay.
it
Okay, no,
depends.
well, I will do the calculations.
Yeah.
I think it's a quadratic.
Yeah, it's a quadratic, but in general, I mean, quadratic but non-trivial. So you have the propagator of the Gaussian plus sine or cosine.
Yes, but you have this representation
so
of
probably it
Caron
can
and
be done.
Loewe,
You
which
can diagonalize the
naturally-
operator via
Yeah.
the same
Yes,
representation.
yes,
Okay,
yes,
okay, thank you.
Now that you have the full distribution, you can go much beyond moments and do something like maximum likelihood to determine the value of h, say, the Hurst exponent. Have you tried
so-
going in this direction?
Yes, we did it with Diego Krapf and also Christine and many others. Experimentalists, actually, were reanalyzing the curves they get in terms of this approach.
And is it better than just looking at moments? I mean, do you get better discriminatory power? when
I
you
would
have the
say
entire distribution?
I would say that this is complementary because still behavior of MSD gives you a hint what is it, at which time stage it is because even super diffusive processes can show subdiffusive behavior at some short time scales, but then eventually develop something which goes faster than t. I would say it is complementary. It's not an independent approach which will tell you everything by itself. So better to know also the behavior of the MSD.
Any other question, Deepak?
So in many experimental plausible realizations of fractal Brownian motion, the origin of time is not very clearly understood, and also the origin of the displacement variable is also not so well understood. So can you make some comment about that?
Yes, definitely. Definitely, the origin of time is ill-defined for the process with memory, and that is why typically people start let the system to cook itself for some infinite time before. But if you look on the spectral densities, it does not change anything. Whether you pre-thermalize the system within an infinite time.
Any other question? No, so thanks, Gleb, again. Thank you.
Thank you again very much.